Okay, Assalamualaikum and good morning. My apologies starting a bit late because I'm still typing out the notes. So I have not uploaded as yet. And today probably we have a shorter than 2 hours because I only had a few hours of preparation last night. We'll see how it goes. Okay. Also, the other thing is, yesterday the Wi-Fi seems to be unstable, so you need to let me know if I get disconnected, okay? Because I cannot see you guys. You can no give me a message or something, okay? Right. So let me go to the lectures. So let me try to recall where do we stop. Right. So I think we have come through this, the second law, the different statements, and also I believe we have done this, the Carnot. Where do we stop? Do you know? Previously, I think we have introduced the Carnot engine, right? And okay, so I think we have stopped somewhere here. I remember saying something about the refrigerator, or sometimes it's called a heat pump, okay, which is the Carnot engine. Here's an abstract representation of a Carnot engine where you have a heat bath at certain temperature above, which is considered hotter, theta1, and then you have another heat bath over at the bottom, which is at temperature T2, lower than T1, theta1, sorry. And this Carnot cycle will take heat from the heat bath at this temperature, which is the hotter temperature, and then do some work and then release the energy from the system, okay, to another heat bath at a lower temperature. Okay, so that is essentially the picture of the Carnot engine that we have introduced earlier. So the ones that we actually do was actually going through all this process using gas expansion, and then this is also expansion but adiabatic, and then you have compression and then compression. Are people getting in, right? Okay, so we have done that, and then I mentioned that Carnot cycle being composed of reversible processes. Down. So one could essentially reverse the process, okay, in a way that, okay, instead of just if I can do this, so one can actually reverse the process because each of the processes in the cycle are reversible. So one can reverse the process so that this becomes taking off, oops, taking off heat from the reservoir or the heat bath at temperature T2, and then one again to work, but now this is actually doing work against the system or for this on the system, and then it goes up to the no, you release the Q1 back to the hotter reservoir theta 1. Okay, so this is precisely what we have mentioned before. When you reverse this, this is really what we call a refrigerator. No, essentially that's how our fridge works, or sometimes it's called a heat pump. Okay, so now let's consider playing with this idea of putting Carnot engine with with other heat engines. Okay, so you can have heat engines which are not Carnot engines. Okay, Carnot engines are the sort of the ideal one because you have composed the cycle in a way given by reversible processes. Okay, so one can think of instead of another heat engine which is not the processes involved is not really reversible. So we call this as a reversible irreversible engine, and you can couple this irreversible engine to the Carnot engine. Okay, so this is the picture that we want to describe over here. So we have this irreversible engine taking up heat from the reservoir on top at theta 1, temperature theta 1, and then release Q2 dash. This is Q1 dash. Okay, it's not very visible, but okay, to make it clear, Q1. Okay, and this is Q2 dash. Okay, this is to take this heat from this reservoir and then convert it to work. Okay, probably some mechanical work energy or something like that, and then release back to another reservoir at a lower temperature theta 2 with the quantity Q2 dash. And what can be done is essentially you can make this work done as the work done on the system for the Carnot engine. Okay, remember earlier we had the picture over here. So you have this work done on the system so that it reverses the process over here to go to the from the cold body to the cold reservoir to the hotter reservoir, so it becomes like a fridge. Okay, so you can do this using this irreversible engine, and it does work onto this Carnot engine so that it reverses this particular what you call heat flow. Okay, and we assume that there is all the work done by this irreversible engine is only on this Carnot engine, and there's nothing else. Okay, meaning there's no other work done by the irreversible engine. Okay, so one could now compare for example, the two engines each efficiency. So in this particular case, we recall our definition of efficiency is just simply the work done divided by the heat input. Okay, and if one consider that the original Carnot engine over here, which is something like this. Okay, instead of reversing here, you have Q1 here, 2. So this is theta 2, this is theta 1. So if you compare this efficiency with the Carnot engine's efficiency, we want to see that okay, the Carnot engine is actually much more efficient than that. Okay, so that's our at least at this point is our claim. Okay, so okay, remember that this is this definition is coming from this picture. Okay, so you're comparing this picture of the Reversible engine with this picture of the Carnot engine. But in this context, we have this whole system as a heat engine altogether. So you can have this couple composite heat engine. Now, as I mentioned, we want to prove that the Carnot engine is the most efficient, and that implies that irreversible engine cannot have a greater efficiency. Okay, so how do we prove this? So we have to prove this by contradiction. So we assume first, okay, the efficiency of your irreversible engine, eta I here, okay, is greater than the Carnot efficiency of the Carnot engine, which is written as eta R. R means reversible. Okay, so what happens in that particular case? Then you should have, by definition, W on Q1 dash greater than W on Q1. So if this is greater than that, okay, remember that W over here is, we are comparing the same amount of work, okay, so that means over here Q1 dash, if this is, the whole thing is bigger than that, Q1 dash has to be smaller than Q1, okay, so you get that. Now if that happens, what's gonna happen, what's the effect gonna be is that, okay, I have taken Q1 dash, the heat from the hotter body, and then go to this what you call process, and then replace back what was the thing I mentioned? Sorry, Q1 dash is less. Okay, sorry. Q1 dash, I was getting confused. Q1 dash is less than Q1. Okay, you should remember that. So now what do? We, in this particular system, we take Q1 dash from the hotter body, dump Q2 dash, and then this process will now dump back Q1 into the hotter body, but Q1 is bigger than Q1 dash. So in other words, effectively, the process over here, in a way, is the net effect is, since this is much greater than that, okay, the net effect is that this is taking heat from the lower reservoir to the and dumping it back to the hotter reservoir. Okay, so in other words, what happens is you have a colder body, you take the heat from there and you dump back into a hotter body. Okay, so that's what happens. Okay, in a way it looks like a fridge, but then you have to remember, you have to do work, okay, to get a fridge. Okay, but here you the whole system, okay, the whole system does no work from outside. Okay, so there's none of this. Okay, so in other words, what you have a system that says that, okay, I can take now heat from the colder body and dump it to the hotter body, which is not the, no, it violates the Clausius statement of second law. Let us go back where Clausius' second law is. Yeah. So you recall that it's impossible to construct a machine which operates in a cycle and produce no other effect than to transfer heat from a colder body to a hotter body. But now we are actually doing that. If we assume, where was the assumption? If we assume this, okay, so the effect is taking heat from a colder body to a hotter body with no other what you call work being done from the outside. Okay, and that sort of violates the Clausius statement of second law. Okay, so you arrive at a contradiction. So the premise that we had earlier, that the efficiency of your irreversible engine is greater than the reversible engine, which is the Carnot engine, is actually false. Okay, so there can be no such heat engine transferring heat from a colder body to a hotter body without any work being input into it. Okay. So so we have now essentially, so that means the true premise should only be eta r less than eta I. Okay, so this is true. Okay, and this essentially established what we call the Carnot's theorem, that no engine operating between two given reservoirs can be more efficient than the Carnot engine operating between the two same reservoirs. Okay. Now, that only is the scenario that we built up was to couple we couple the irreversible engine with the Carnot engine. Okay. One could simply ask, can there be two different Carnot engines, one being more efficient than another? What's going to happen? Somebody coming in? So what's going to happen in that particular case when, well, we can do the same kind of picture again like the one before. Okay, we have this. So here is an irreversible engine, and then you couple with the Carnot engine, which is doing the reverse operation. So we can do the same if your efficiency of one Carnot engine is different from the other. We can also do the same. Okay, it's the same picture, just with instead of irreversible engine over here, no, you just have another Carnot engine which has greater efficiency than that. Okay, so if this is possible, then the same kind of argument will occur, because in this particular case, Q1 dash should be bigger in a way than Q1. So what was it? Oh, sorry, Q1 dash is less than Q1. Okay. So then you will be able to get this process again of transferring heat from a colder body to a hotter body. So again, we cannot have that unless, so the assumption here is that, in general this could be true, because you can, here I don't make any differentiation between the two. I can have, this Carnot engine, I can have this picture in reverse instead. Okay, let me draw that. So I will have Q1 dash here, because both of them are reversible, and then this is Q2 dash, and work being done the other way around. This will be down. Okay, so now it doesn't matter which one is doing work against which one, right? So in other words, you just need to have this supposition in a way to get the contradiction. So if you have Q1 dash different from Q1, it doesn't matter which one is bigger from the other, you will simply get your contradiction again. You either have this picture, okay, this picture, or this picture. So in other words, having this condition will give you the contradiction, no matter what. So in other words, the only way, so in other words, this supposition or this premise, okay, has to be false. So what's the true premise then? The true premise then, it must have the same efficiency. Okay, so the efficiency is actually here, but that implies that. Okay, so all Carnot engines will have the same efficiency. Okay. Some mistake there. Everything done in a rush. Okay. So now what do we say? We will say that, okay, since the efficiency is going to be the same for all Carnot engine, then the function of the efficiency, so this function, for example, must be a universal function. So it doesn't matter what Carnot engine it is, okay, this function will be the same. So this will be a universal function. A universal function of what? Universal function of the temperatures. The temperature is a state variable. Okay, so in this case, state variable temperature and pressure. Okay. So having said that, now, okay, temperature there are two. Okay, I've forgotten to mention, because you have the two different heat reservoirs. So that means I would really have to have theta 1, theta 2. Okay, so it will be a function of a universal function. That means it's the same function for any Carnot engines. Okay, or no, this is actually already a constant in a way. Okay, so the universal function now applies to this ratio. Okay, so now we claim that, okay, there is a universal function operating as the function of this ratio of Q1 and Q2. Okay, so that is the thing that we want to emphasize at this particular point. Okay, right. So what do we do next? Well, recall, why are we doing all this? Recall, let me go back, so that you have a clear picture of where we are going to go ahead. Recall, because you don't have the notes yet, so that's why I have to recall back what is the thing that we want to do. What was it? Yeah, this is the idea is we want to define this idea of absolute temperature given something that you know about entropy. Okay, we go through these several steps. We use second law in the context of heat engine, which I already looked. There are two different statements, Kelvin and Planck, and then the other one is the Clausius one, which we already implemented there just now. And then Carnot engine being the most efficient engine. Okay, we have done that. So now what we want to do is to say that, okay, from that we can actually define a new temperature scale, which is going to be called the absolute temperature. Okay, these two will have to be done in probably in the next lecture, because I have not prepared the notes for that. Okay. So we are now at this stage. Okay, so right, so how do we do this? So let's go back down again. Are you still there? I need to check out. You're still there, okay? Right, because I'm just afraid, like, what the lecture yesterday I had, it was disconnected several times. So, right. So, where is it? Okay, so we have done this. So the next thing to do is to define the absolute temperature. Okay. So what do we do? Now we run two Carnot cycles between three different temperatures. That means we have between temperature theta1, theta2, and then we join this with another Carnot cycle operating between theta2 and theta3. Okay, so basically there are two Carnot engines coupled together in a sequence. Two Carnot engines coupled in a sequence. So it's different from the one couple before, which is actually in a cycle. Okay, so this is coupled in a sequence. So effectively, I can think of the whole thing as another Carnot engine. Okay, here I'm thinking of the Carnot engine, one Carnot engine operating between theta1 and theta2, and then sequentially another Carnot engine going from theta2 to linking heat bar theta2 with theta3. Okay, so here we assume that theta1 is greater than theta2, then theta2 is greater than theta3. Okay, so one can think of now the whole system, the composite Carnot engine, is actually operating between theta1 and this lower temperature theta3. Okay, so and you remember that, okay, previously we already have this a condition of being a universal function, so we're going to use that. Okay, so in other words, that function has to be the same for any Carnot engine, right? And here you have two, in fact three. Okay, the one Carnot engine over here, another Carnot engine over here, and then the composite Carnot engine. Okay, so you have three different Carnot engines in play here. Okay, so in other words, if one looks at this, say the composite case, then you have this ratio. Okay, we should have the same function as before, right? But I can think of that ratio as the ratio between Q1 and Q2, and then multiplied by ratio of Q2 and Q3, which is the individual pictures over here. Okay, so this will be the so this will be F, this also will be F, and this will also be F. Okay, so how can this what does this imply? So it will just simply implies that, okay, this one is operating between what temperature and what temperature. So this is between temperature theta1. Okay, remember the temperature is the state variable here. This is between theta1 and theta3. Okay, this one is between theta1 and theta2, and then this one is from theta2 to theta3. And whatever this function is, okay, it must obey this. Okay, so how can this happen? Well, this can happen if this function itself is a ratio of functions of the individual temperatures. Okay, so you write it this way. So then you have phi theta 1, phi theta 2. So phi, since this is a universal function, so this will also be some sort of a universal function. Okay? So then you have f theta 1, theta 2 given by phi theta 1 divided by phi theta 2, and f theta 2 and theta 3 will be phi theta 2 divided by phi theta 3, so that when you might try to do f theta 1 theta 3, then you expect the same function given here to be phi theta 1 divided by phi theta 3. And you can see that this sort of thing, okay, obeys that relationship. Okay, so finally we come to the point of saying, okay, I have this relationship which just your heat ratio of heat are just the ratio of your function of the temperature. So what Kelvin asserts is to define this function, which is a universal function here, to be your absolute temperature. Okay. And the ratio of heat flow in a Carnot cycle is really equivalent to the what you call the ratio of the temperatures but remember that the temperature is generally is an arbitrary function, but now this becomes an absolute temperature because of the assumption of the universal function. Okay, so in a way what we have done is to make use of the Carnot cycle to act like a thermometer. But generally this is hard to do because reversible cycles are really ideal processes, okay, and they are quite difficult to realize. But for the case of the ideal gas, or sometimes it's called perfect gas, okay. So there are two names for this. Okay. And for ideal gas, you know many things about it. Okay, many things about it, and you can actually do make quantification of the processes involved. Okay, so we go back to this idea of Carnot engine using the perfect gas, where you have the compression of gas, expansion of gas, and then compression of gas. Okay, so we'll try to look at this and try to use all the laws that we know about perfect gases. Okay, so the first thing that we need to understand is that the internal energy of perfect gas only depends on the temperature and the number of moles. Okay, so then if you remember, you have this first law. Okay, it's the work. Then since we are asserting that your internal energy only depends on temperature, then for an isothermal process, so where are the isothermal process over here? So the isothermal process is this one from between A and B. So this is isothermal. So let me just do that isothermal A and B, and then C to D, and then the other curve is actually adiabatic. What's the other one? D2A. So then for the isothermal process, for example, the case of AB, okay, you have this. Okay, because U only depends on the temperature, and we assert that we are only using a fixed number of moles over here. Then the only since isotherm means the temperature stays constant, so there is no other thing that can vary it. So this is actually equal to 0 for isotherm. Okay, so then essentially what you have, the amount of heat is equals to the mechanical work. So one could actually integrate this, okay, because you know you have this relation from the first law, but you also know that what was that? P equals to nr theta divided by V. Okay, so this is ideal gas equation of state. Okay, so one can use that now to integrate between this points in the cycle, well, points in the process of the isotherm. So over here, then it becomes, since we are writing it in terms of variables theta and V, and the one that's changing is really V, so you are integrating between the points of A here is given by the volume VA here, and then B here will be given by the volume VB. So you need to integrate that, and you know how to integrate that. That's just giving you the log function, the natural log. And theta 1 is actually fixed because we are looking at this isotherm. So this isotherm is at temperature theta 1. Okay, and then you do the same. The only difference over here is here you're thinking of Q1 goes into the system. Okay, and here Q2 is escaping the system. Okay, so in a way that is supposed to be a negative sign there if you think about it. Okay, then to counter that negative Q2, okay, then I just simply reverse the path again. Okay, instead of going from C to D, okay, which is the process that you do in the cycle, I'm just considering just like the previous case. Okay, I have A to B, okay, and then here will be just D to C, and this becomes Q2 going into the system. Okay, so then you have a comparable thing to calculate. So you essentially here I already reverse. This will be the initial volume, okay, and this will be the final volume. Then you get again the same formula there. Okay, so you have VB, VA here, VC, VD. So now this is actually Q2 and that is Q1. So I take the ratio between Q1 and Q2 because that defines our absolute temperature there. So then I will now have theta 1 log VB over VA and theta 2 log VC over VD. Okay, there are two different temperatures here. So here is the absolute temperature. This one is coming from the gas temperature. Previously it was noted as theta G. So this is gas temperature. Okay, they are different in a way. Okay, different, but we are going to show that they are the same. Okay, the same in a relative context. So so what do we do now? We still have this problem because this is this is something we do not know how to relate between each other. So but then we have another thing that we have not used inside this Carnot cycle. Okay, Carnot cycles are not just the isotherms, but you also have the adiabatic process. Okay, so we can use adiabatic process, and we have learned adiabatic process before for the case of the perfect gas when we discuss about heat capacities. Okay, so we know that perfect gas or ideal gas will behave in such a way that theta gas temperature multiplied by your volume of the gas to the power of gamma minus 1 will be constant. So you can look back, I think, the second lecture, if I'm not mistaken. Okay, so then what's gamma? You might recall gamma is essentially the ratio between the heat capacity at constant pressure divided by heat capacity at the constant volume. So in other words, in the case of the process B to C, then you should have that. Okay, because it must be constant for adiabatic process. Similarly, for the process dA, you also have the same thing. So now what happens is that we have this relationship between the different volumes, and you can actually use that. So I can now, for example, see that the fact that I can rearrange these two equations to give you the ratios of the gas temperature, theta 1 divided by theta 2, here also theta 1 divided by theta 2. So I have these ratios of the volumes to be equal. Okay, and remember that we're still having these powers, but then you can actually show that, okay, the ratios in this case is slightly already what you call rearranged. Okay, the ratios of volume C to volume D is equals to volume B to volume A. Okay, that's almost done the job, but our thing over here is actually involving log, but that's no problem. We can take the log of that particular equation. Then you have log of VB divided by VA equals to log of VC divided by VD. Okay, so plug all those things in, and then you'll find that, okay, I have the earlier equation, which is that. Okay, this is our earlier equation. Now we reduce that to this using the adiabatic relations. So finally, what does it say? Okay, it says the ratio of the absolute temperatures is actually equal to the ratios of your gas temperature. So effectively, that only says it's not the same scale, but it is proportional. Okay, it's only proportional to the gas temperature. So here we have an option what to set your reference temperatures to start with. So we already have a standard in SI, the so-called metric system to start with. The standards is to use the triple point of water, where your your ice, phase of ice, water, and vapor coexist. Okay, and they coexist at this point called the triple point of water, and that will be set as a reference point or the reference temperature. And once you do that, one gets what we call the Kelvin scale. Okay, so the Kelvin scale now describe our universal what's the word? It's not universal, it's the absolute temperature, sorry. absolute temperature. So, okay, I've come to the end of my notes. So, yes, scale. Okay. So that is, so we go back to this picture earlier where we try to see the processes of the things that we want to do. Where is it? Oh, some below. Yeah, this one. Okay. So we have essentially reached to this particular point. There are two more points that we want to discuss, which I have not prepared the notes, so I will not risk myself of putting down things that I do not really understand. So I will just delay this further to the next lecture. Okay. So I will upload this set of notes. Okay, so this will be lecture 3. This one will be lecture 4. So I will upload lecture 3 first, and I will continue to do the lecture 4. So hopefully you can be patient with my note making, because essentially I do not have ready notes for this particular course. The last 2 semesters I was actually using a different book. Okay, so we'll end up early today if that's all right with you. Okay, so we have a short day today. Okay, so I will take the attendance now. Okay, that's done. So thank you everyone. There should be a assignment coming up soon. I wouldn't want to promise when, but no, there will be one assignment in this near future. Okay, thank you everyone. Okay, bye.